Projections are a way to describe how one vector relates to another. We're going to picture in the plane, the xy plane, a vector b that's given by the magnitude of b times the cosine of theta, the magnitude of b times the sine of theta. Theta being the angle made with the positive x-axis. And what we've just written down here is that the x component of the vector b is given by its magnitude times the cosine of theta. Another way to say that is that the part of b that points in the direction of the x-axis has a length of magnitude of b times the cosine of theta. We can make a similar assertion about the magnitude of b times the sine of theta is the component of b in the direction of the y-axis. Now I've taken this vector diagram here and I've rotated it so that what had been the x-axis is pointing up a little bit, I don't know, maybe 20 degrees, doesn't matter. And the vector that had been b is now pointing further in the y direction. I'm still going to call it b, even though it can't possibly be the same vector because it has a different direction, but the lengths match. As does the blue shadow kind of underneath the vector b in the original diagram. That matches the length of this blue, what is now a blue vector, on the rotated, had been the x-axis. For ease of speaking, and because I know what we're developing here, I'm going to call the rotated x-axis-ish thing A. So we have a vector A, we have a vector B, and the blue kind of shadow on the vector A from vector B actually meets the vector A at a 90-degree angle, just like the shadow on the x-axis it was a 90-degree angle up to the head of the vector B. Okay, because I rotated this picture to make this new one, the angle between the two vectors hasn't changed. And so it's still theta. That's now the angle between A and B. The blue portion that's projected onto A has a length of magnitude of b times the cosine of theta, just like it did in the previous picture. I was trying not to use the word projection a minute ago because we hadn't really introduced it, but that's the best way to put it. In the previous diagram here, b projects onto the x-axis with a magnitude of b cosine of theta. Likewise, in the rotated picture, b projects onto A with the same length, magnitude of b times the cosine of theta, the angle between them. The length of the projection vector is the scalar projection of b onto A, and it's denoted comp b subscript A. And that comp there is the component of b in the direction of A. Just as we have a component of b in the x direction and the y direction in the original diagram here, we can break down b into a component along A. But remember, we have this dot product representation. A dot b is equal to the magnitude of A times the magnitude of b times the cosine of theta. So I can solve for the magnitude of b times the cosine of theta, and we end up with A dot b divided by the magnitude of A is equal to the magnitude of b times the cosine of theta. Therefore, we can say that the scalar projection of b onto A, which is comp b subscript A, so the component of b in the direction of A, is equal to A dot b divided by the magnitude of A. That's the scalar projection of b onto A. Things tend to be confusing like this sometimes when there's a b and there's an A, and on the right-hand side there's a b and the A and then an A. And so what I would say is the one that's the subscript A is the one that shows up in the denominator as the magnitude of A. So that gives the length of the projection vector. if we go back and look though, there's an actual projection vector, right? And we have it in blue. The projection vector itself has the same direction as A. We can see that because it's lying on A, and length component of B in the direction of A. This is written as projection of B onto A, so proj instead of comp. And we need it to have the same direction as A, so at some point we're going to multiply by the vector A. But it has a length that is the component of B onto A. In order to ensure that I'm only talking about the direction of A, I'm going to divide A by its own magnitude, so we end up with a unit vector. To ensure that the length is correct, the component of B onto A, we're going to write down the expression we just saw, A dot B divided by the magnitude of A. That gives us the length. We can combine the denominator. We end up with A dot B divided by the magnitude of A squared times A. That last bit is what we call the vector projection of B onto A.